Good morning, and thank you for being here on our last class day. We will see you all again next Thursday night for the finals. That'll be our next meeting. I will send out an announcement. I got to look at my schedule, but I believe it's about 3 o'clock on Tuesday afternoon that I can hold a Zoom meeting. So I'll put that out there if you have any questions. So the goal is that you work through the review stuff for the final. And basically, it involves going through test one, test two, test three. Again, going through those reviews. If you understand them well, that's great. You'll feel very much at home on those questions. But anything you missed or didn't really understand, that's what you want to go back through. So there's quite a few resources in there. I've got some solution guides, some videos of me working through some of the problems and the reviews from test 1, 2, and 3. Again, practice on those. And always, it's a good idea, certainly, to practice on what you struggled with, but it's also a good idea to go back and take a look at those that you did well on and tell yourself, I know this stuff, right? Builds that confidence, because you want to come in with some confidence. Not overconfidence, but know what you know and know what you're struggling with. It's been those times, but remember, you've made it quite a ways. You made it to the end. Not everyone's made it this far. So that's awesome. And you've done it with your own effort. And again, hopefully I've provided some good resources, but you're the one who's learned it. So that's an important thing to remember. So there's all these things. There's some study guides. You'll see video solutions. There's a review for the final exam from spring. They're basically the same. I do have the final exam copy. There will be 10 multiple choice questions and 7 open answer type questions. Okay. No, let's say, because I looked on my phone and it didn't show everything, but I believe it's just the 10 multiple choice. I don't believe I saw any true false. I hate true false because a good one has to be tricky, and since it's tricky, it's not a good question, right? Can't be too obvious. But even the multiple choice can be. Just to get in advance, I'll tell you the night of the exam, but I've got from the community college I work with as well, they use this thing called ZipGrader, which is a phone app. So I'm going to have a special Scantron form for you that if you'll fill that in, and I'll be able to grade the multiple choice a lot quicker that way. Not only that, the app allows me to put in which questions I give partial credit for. So it works really nicely. I'll look in advance and say, okay, this one should get like half credit because it's almost right. So I'll do all of that, and then you'll fill that part in, and those 10 questions will get graded a lot quicker, which means I can get to those quicker too, because we get done on Thursday night. I'm out of here Tuesday the 12th, so I got to get everything done, and I'm moving at the same time, and so I got to get things done quick just for myself, so I get your grades posted and get those to you. And I like to have them all posted as much as I can in advance, so you can take a look at it if you have any questions before I actually post them to the transcripts. Okay, so our last section, 14.5. We are recording, are we? Yes, we are. This is something called improper integrals. Okay, so these are some applications. What you're going to see is there's a couple different times this improper happens. Is basically when the area kind of goes off to infinity. And then we got to decide what happens. Sometimes the area also goes to infinity. We call that diverges, and it really doesn't help us. Sometimes, though, the amount of area becomes so small, the additional area, that it actually what we call converges. It goes to a number. We can say, oh, this equals 2, or this equals 50, or whatever. We can actually come up with a number even though it's going off to infinity. Okay. The application in business for this, as you'll see, is whenever we have to make a decision, but we don't know an end date. It might be 2 years, might be 3, maybe 10. We're not really sure. So we do an analysis with infinity as the end date. Sounds kind of weird. but it'll allow us that, hey, if we go to this limit, this is about what we're going to get. Okay. And it works well if there's like a decreasing returns or something that eventually it trails off, and we can say it helps us with those indefinite decisions. We know sometime in the future we're going to have to switch from vinyl records to CDs, or then we went from CDs, and that's the example we have, going from CDs to downloaded music. Do they even sell new CDs anymore? I've been to records. I don't even, do they even have record stores anymore? It used to be a big deal when I was in high school. Yeah, I'd go down and buy a record. Now you just download them, right? So that's the application. What you're going to see is nothing new mathematically. We're going to take integrals like we've been doing. So it gives us practice with the FTC, the fundamental theorem of calculus, which is a big word, a big phrase, but we'll see it's just integrate it, get the antiderivative, and plug in the boundaries. What it will do is it will connect us all the way back to where we started with 10.1 and 10.3 on limits. So I'm going to, in fact, I've got a slide in here from 10.3 that will remind us about that. And there's really only two limits we need to consider with. So let's go ahead and get started and see where we're at. Let me get my writing utensils again. Here we go. Now we're back in business. Okay, so hopefully everything's working again. So we've dealt with this definite integral. Okay. We're going from some beginning point A to some ending point B, and we've got a closed interval, which means that A and B are both included, and we can integrate this. We get the antiderivative, right? And so f of x, remember, was like a derivative, and so we integrated it, and we got the function it came from, which sometimes we called big F, and then we went from A to B, and this is the fundamental theorem of calculus. So sometimes they'll ask you to use the fundamental theorem of calculus, and you don't remember that word or that name, but this is what it is you integrate it, right? So this is integrating, and then you take the new function, the integrated function, the antiderivative, from where you plug in the upper limit minus the lower limit, and that gives you the value. That gives you the area under the derivative curve, right? So that's the fundamental theorem of calculus. That's what we're going to do. The only thing that's going to be different is A or B might not be a number. They might be infinity. Well, in fact, they will be. That's what we call an indefinite integral. The PowerPoint, which comes from the textbook company, will show a lot of mathematical symbolism and using the limit functions. I'm just going to use the symbol for infinity, so I'll show you that way, and we'll go from there. Okay, so integrals with a limit of integration is infinite. So this is one type that we're going to look at, and then we'll look at one other. Okay, so notice instead of going to B, it's going to infinity, positive infinity. Or instead of starting at A, it could start at negative infinity, which again, in business sense, that might be, oh, we've been doing this so long, we don't remember when we started doing it. So let's just kind of integrate from infinity. So these, again, the application is not really infinity, that we're trying to go back to the very beginning of time or something, or past that time, but it's just we don't know how long ago that was, so we use infinity either at the beginning or the end. Or there's also this one, but I didn't see any of these in the homework. This one you have to actually break it into two pieces. You break it into basically this one and this one, and you integrate both of them. But we're just going to deal with one or the other. There is an example of the first one and an example of the second one in the homework. But we work them both the same way. Okay. And again, what it does say, what does infinity mean here? Does it mean forever? Well, it means that we're taking a limit as something gets large. And again, in our business applications, a lot of times what's getting large, that variable is time. It's sometime in the future. And it's large, but we don't know how large. So that's what we're going to call infinity. Okay, two things can happen. Only two things. It either converges, which means it kind of stops getting bigger and goes to a particular number. That's what we mean to converge. It goes to a particular value. Or it diverges, which means it goes off to infinity, or it's undefined, or something like that. We can't calculate. We can't get a number for it. That's diverges. And in the homework, the cool thing is the first question is, does it converge or diverge? And you just click on which one. If it diverges, then you say, does that the limit itself does not exist. Of course, knowing that it diverges is, we'll be able to take a look at that. Okay, we could always try it, and if you get it wrong, then you know it must converge, and then you got to find something. So remember, you get the 5. Although that one only gives you right because it's only 2 questions. It's either right or wrong. So, but we'll work with it. But the part of whether when it converges, then it's going to ask you what does it converge to, and that's what we're going to work through and see. Okay. This is from 10.3, so this takes us all the way back to the beginning of the class, and hopefully it makes a little bit of sense now. What you'll see is most of these, this is determinate, indeterminate forms. This was from limits, right? 10.3 limits. What you'll see, most of these are diverging. So if we get any of those, it's going to be diverging anyway. So what I do is I concentrate on, there's actually only 2 up there that converge. These 2 converge, everything else I can say is going to diverge, right? So the ones we want to focus on is this one here. So if I've got k, which is just any number, something divided by infinity, remember if you divide, if the denominator gets bigger and bigger and bigger, it actually, the whole number goes to 0. So that's one that we're looking to. So it'll go, that part goes to 0. Okay, so dividing by infinity means we're going to go to 0. The other one is down here, and that's if we have something with an exponent on it, a negative exponent that goes to, so it's going to negative infinity, that also will go to 0, right? Because that negative infinity means we're dividing by a larger and larger number, which makes the number go to 0. So those are the only 2 we have to remember, right? Those will converge. Everything else you see up there is going to infinity, I think. They give you some things over here. But yeah, so this one, so an exponent that goes to positive infinity, that diverges. Boom. So there's only these 2 that we're going to worry about. And again, I'm going to kind of just take a shortcut through all the notation, not worry about all the proper notation, just getting to the proper answer, right? Because again, in math, if you're a mathematician and you're going to be a math teacher or something, all this other stuff seems to be important to them. But to me, it's like, let's get it first, and then we can talk about how to make the notation nice and all that kind of stuff. Okay, so this is the notation stuff. If we going from negative infinity to b, so this is an unknown start place, they just replace the infinity with a letter, any letter you want, and then they use this limit notation because it's, mathematicians think it's kind of vulgar to just say it's going to infinity. Say, well, oh, the limit as it goes to infinity. I just say, let's go ahead and be vulgar. Let's just put in infinity, okay? Same thing with the A part, which we already talked about. And notice if both ends are going to infinity, again, which is not a case we're going to have to deal with, but you would break this into 2. The starting, going from negative infinity to some part, and then going from some other part to infinity. And usually that middle part would be something like 0. But again, we're not going to deal with those, so we won't even talk about it too much. We'll just talk about these 2 cases here. This one and this one. I guess I skipped over this, but we're not going to use this limit notation. We're just going to go ahead and stick infinity up here and then plug in infinity. And then remember, we just have to compare it to the 2 that converge. We either end up with 1 over infinity, oh, that goes to 0, or we end up with infinity or some number to the negative infinity, that will converge. Anything else, oh, it diverges and we're done. Okay. It diverges and we're done. Okay, now this one had it's all here. The reason I leave it here, I forgot yesterday, I forgot why I left it all there, is because it's got all their notation, but I want to show you how I would work it. So I would go with this, I would rewrite it as 1 to infinity, positive infinity if you want. I will rewrite the x to the minus 2, or x over 2 to x to the minus 2. You know, so I sometimes talk backwards. I say what I'm thinking, but x to the minus 2, because it's 1 over x squared, dx. Okay, we can get the antiderivative, right? So what we do is we add 1 to the exponent, right? So we're going to add 1. So negative 2 plus 1 is going to give us x to the thank you. I was going to go positive 1, but no. Negative 2 plus 1 is negative 1 still. And we have to divide by that new exponent, right? Divided by negative 1. And then the fundamental theorem of calculus says we're going to take this from going from 1 to positive infinity. And notice I'm not using limit notation because we're going to see we really don't need to. Because we're just going to compare to those two cases. And so fundamental theorem says I plug in the infinity first. I'm going to rewrite this as 1 over x because it'll, I don't know, and then this negative can just come out front. So this, what I'm going to do, I'll show you. I'm going to do negative 1 over x is how I will interpret this, right? Take the negative exponent, put it down. So this becomes negative 1 over infinity. Notice I'm just going to plug in infinity instead of put this limit of and all that kind of stuff. And then I subtract when I plug in positive 1, so that's negative 1 over positive 1, right? I'm plugging positive 1 in for the x in the denominator. So what happens to this? And again, we are thinking limit. When I take negative 1 divided by infinity, what am I going to get? 0. That's one of the two cases. That's 0. Okay, I know what 0 looks like. Minus, what's negative 1 over 1? Well, that's negative 1 and a negative, so that must be positive 1. Does this diverge or converge? It converges because it goes to a number, and that number is 1. So we got both things here. So notice you don't really, until you get to the end, you won't know necessarily whether it converges or diverges. You have to kind of work through. But what we would say that this converges because it's going to a number, and what it converges to is 1. So we get both answers at the same time. Had that not converged, had it gone like to infinity, then we would say it diverged. And then we would say the limit does not exist. I think we've got one of those. We'll make one up. We'll bring one from the homework that does that. Okay, does that make sense so far? And again, you can see how the book works with it, with using all this mathematical notation. The limit as m goes to infinity. Where did m come from? They just made it up. Why not just keep it infinity? That's my thinking. Because we only have two cases. So, something divided by infinity, that goes to 0, and then we got the exponent. We good? Questions? Okay. Now we'll go through a problem, and actually I'm going to work this different than how they did, but because I'm going to do what they said they're going to do, so we'll see. Okay, so here it is. By 2009, music downloads were making serious inroads into the sales of physical CDs. Most of you were born before 2009, weren't you? Sometimes I forget about these numbers, and wow, yeah, talk about 1980. Most of you were not born in 1980, right? That's when I graduated from high school. And I'm sure none of you were born in 1962. No, I was. But in fact, actually, this year, someone told me this. I saw this, that this year, 2023, your age and the year you were born for everybody is the same. So I'm turning 62, and I was born in 1962. So think about that. What year you were born? I don't know if it applies if you were born after the year 2000. Maybe not. Yeah, because 2001, you're not 1 year old. But I think, oh no, that can't work. There was something about that. Anyway, I'll see if I can find it. But I was stuck on 2000. I'm 62, and I was born in 62. That was kind of cool. But yeah, if you're born in 99, you're not 99 years old right now. So that I must got something mixed up as usual. Okay, so approximately 290 million CD albums were sold in 2009, and sales declined by about 23% per year the following year. Oh, I guess maybe this is so 23% per year. When I worked this one, you could see the video from yesterday. Is I read this. Suppose that this rate of decrease were to continue indefinitely and continuously. So that told me continuously decreasing, right? Continuous decreasing is going to be a special formula. Continuous interest is PE to the RT rather than the periodic. They're going to use the periodic, so they're going to take 100 minus 23. They're going to use 0.77%. But I'm going to go with this route because I read this continuously here. But then I see, yeah, it's 23% per year. So I guess I was saying yesterday that the textbook was completely wrong, but now when I read this, I said, okay, they could go that route. But I'm going to go this route just because I see this continuous. I shouldn't have said this, okay? How many CD albums total would be sold from 2009 on? So what we're going to do is we're going to integrate, because we're trying to say an accumulation. The formula we're using is P, which is the initial value, E to the RT. So we started with 290. Our interest rate, our rate is decreasing by 23%, so that would be negative 0.23, and then T would be the number of years. Okay, so that's the formula we're going to use. You'll see that they use a slightly different one. They use, instead of this part, they use 0.77, but we'll talk about that in a moment. Okay, so I'm going to integrate this, and also the problems we give you on the exam, as I've looked through, they all, if we're going to have you integrate a exponential, so far it's always been E, hasn't it? I believe in all the exams, and so we kind of stick with that. So we're going to go 290 E to the minus 0.23 T. We're going to go from year 0, which is 2009, to infinity because it's indefinite. We don't know the end date. Is how we're working this thing, and then we just put our little DT to show that that's an annual rate, annual thing that's happening. So we're going to see if this converges and how we do it. So we get the antiderivative, and remember, e to any power, it's its own. When we integrate it, it's its own antiderivative as well. So that's 290 e to the minus 0.2 or 0.23. Sorry, divided by, now this is a part you want to remember, when we integrate e, the shortcut rule says you divide by that number that's in front, so 0.23. And the shortcut rule, I think, is something like e to the ax. If you're going to integrate that, that always becomes e to the ax divided by a, so whatever that number is. So that's sort of the shortcut rule. You could get it by using that u substitution, but that's overkill. Okay. And speaking of u substitution, that's something you'll want to review. That's always something that's on the exam. So take a look at that again. And then we're going to take this, remember, from 0 to infinity. So now we use the fundamental theorem of calculus. Let me write that, the FTC, fundamental theorem of calculus. We plug in infinity. So this is 290 e to the minus 2.3, oh, sorry, 0.23. I think I just like variety so much, I always like to switch the numbers somehow. That's it. To the times infinity, all over 0.23, actually negative 0.23, minus 290 e to the minus 0.23 times 0. Sorry, it's getting really over minus 0.23. Okay. So that first part, this one, ignoring sort of the numbers, this is e to a negative number times infinity. So what does that become when we think of limits? What is e to the negative infinity? 0. That's one of our examples. They have k to the negative infinity goes to 0. So we just say this, and notice I didn't use limit stuff, but I'm just saying, okay, then it's going to negative because of this negative here. So this is going to go to 0. Beautiful. Then we've got this number. This is e 0.23 times 0. What's 0.23 times 0? Quick. 0. Yeah, that's the one. You get that. I was always proud of, I can multiply by 0 real quick, Dad. 0 and 1 were my favorite. When I was a kid, I was just so proud. Dinner time, watch me. I can multiply by large numbers by 1 or by 0. 0 was my favorite, of course. Dad wasn't too impressed, but he tried to act it out, right? So e to the 0 power, though, now there's another one, right? Anything to the 0 power is 1. Good. Be careful there. You're jumping to, sometimes your mind jumps. Oh, it's 0. No. Anything to the 0 power is 1. So this e to the all of this is all just 1. So it's 290 divided by negative 0.23, right? That's all we got. So it is going to converge. It converges to this number. I've got a negative and a negative, so that'll make it positive. 290 divided by 0.23, which I don't think I have any. Oh, I've got a phone with me. Left my calculators at home. But there's always this one, right? 290 divided by 0.23, and I took care of the negative. That's 1,260.86, or maybe round it to 0.9, maybe 1,261. But remember, this is in millions of CDs. So eventually, basically saying that if this sort of continues, after 2009, about 1,260 million CDs total will be sold between 2009, whenever that future date is. We don't know what it is, but we know that eventually there's just not going to be any CDs because it keeps decreasing forever. Okay. Now we're going to see that their answer they came up with was slightly different, but that's because they didn't use continuous. And I don't know why you would say continuous unless you want continuous interest. At least that's what I saw. But I guess they're going with that it's a per year. The interest is per year, but it's happening continuously. But this is a bad word to use because when you use it in math, that indicates that you should use E. Okay? Just saying. And there's supposed to be math people who wrote this thing, but okay. So we'll walk through their solution, and what you'll see is they're doing basically the same thing. Again, instead of putting infinity, they're using this m, and then they're going to take some limit, right? So they come up with this. And again, all I did differently is I used infinity all the way through. Now they came up with, they're using the periodic interest, right? That it's an annual sort of compounding. So they took 100% minus 23%, and that gave them 77% is what they're getting back. And so that's what the base is here. So they're using they're really using that as an annual rate. Again, I saw that word continuous, and that's where I went. And so it just makes the integration a little more difficult. But again, where everything else I've seen, it's got an e to the power. So when you integrate 0.77, it integrates a little differently. You get this natural log of 0.77 down here, which you'll probably see natural log of 0.77 must be about negative 0.23, because that's pretty close. They plug in these values. Okay, this part, since how did they do that? That's going, because this value is less than 1, so you kind of have to remember a different thing, that since this is less than 1, this actually goes to 0. This one goes to -1, and then they multiply. They come up with 1,110, which is a little bit less than we came up with because we used continuous interest, because that's what they indicated. At least the story I'm sticking to. So is that okay? Again, the method is basically what I want you to see. Now, this is the second case. So we will have, and we'll maybe come back and review a couple different ones. Second case is that the limits are still are not infinity. They're bounds that are numbers, but when we integrate, we get something where we sort of get like a division by 0, or we get something that diverges. Okay, so we're going to look through a couple of these. So one of the things they're concerned with this one is if you were to plug in 0 here, so if you're kind of just finding the area under the curve, 0, square root of 0, 0, you get 1 over 0, that goes to infinity, right? So that causes a problem at the start. What I'm going to show you is I'm not going to worry about it. I'm just going to integrate it, and we're going to get the same answer they did without all their worrying. So the problem is this is what the graph looks like, right? 1 over the square root of x would look like this. From 0, this is actually, this actually never gets there. It's asymptotic, but so this goes off to infinity, and they say, so that's not really mathematically well defined, but we're going to see we actually won't have to worry about this. So we're going to take a slightly different approach. Let's see if I go here. So what they do is they kind of say, okay, instead of putting 0 there, let's put r, and then kind of use limits as we get close. Let me back up here. I'm going to show you how I'm going to do it. I'm just going to integrate this. Okay, I'm not going to worry too much. I'm going to go from 0 to 1. 1 over the square root of x is actually x to the minus 1/2 power, or minus 0.5. I'm going to use 0.5 because decimals are easier for me to work with, right? So this is x to the minus 0.5 power. I'm not going to worry about that. If I plug in 0 right now, I get something that's undefined, because I'm going to take its antiderivative, right? So antiderivative, we add 1 to this, right? Negative 0.5 plus 1 is positive 0.5, right? X to the positive 0.5 over 0.5, which is 1/2. And what you're going to see, that kind of flips over, and that, again, going from 0 to 1. I'll rewrite this. This is really, the 0.5 is 1/2. You take the reciprocal. This is going to be 2 square root of x, going from 0 to 1. Does that make sense? Okay, so that's just the antiderivative. Got it? Now, if I plug in 0, can I take the square root of 0? Of course I can. It's still 0. I have no problems. I don't even have to go to limits like they did. It's like, what are you guys worrying about things? Sometimes just do things and see if you got to worry about it later. Sometimes you worry about things before you even begin. So again, what I'll do is, this is 2 square root of 1 minus 2 square root of 0. It all works. 2 times square root of 1 is 1, so this is 2. 2 times 0, or square root of 0 is 0. 2 times 0 is 0, so it's minus 0. So our answer is 2. It converges, and the limit is 2. Okay? So it didn't cause us any problem. And you'll see that this will always work if you just do the antiderivative. All these ones, they're worried about if you were to try to like graph it and solve it by area under the curve, it doesn't work very well because it's undefined at one of the endpoints. And I think the calculator might even blow up at that, In fact, I hadn't tried it. Well, I'll let you try it on your own. See what the calculator says it is. I think it might have a problem if you're trying to get the area under the curve. But if you do it this way, you're fine, and you never have to worry about that endpoint. So here's what they did, and I'll show you. They got the same answer. They go ahead and integrate it, or they're going to. They got the same answer we did, 2 square root of x going from 1 to r. And they plug in the 1, and then they plug in r, but then they let r go to the 0 from the right. Okay, so it's just kind of like too much technicality. Well, that's just 0. Square root of 0 is 0. Okay, we're all fine now. So I just say, don't worry about doing all this little extra stuff, because if you integrate it, you'll be fine. You know, we were fine right here. We didn't have to talk about limits. We got the same value they did. And if it didn't, and like we had like a negative or something, we were dividing by 0, it would have blown up. We would have seen it going to infinity, or we would have had division by 0, which is undefined, so that diverges. Okay, so we would catch that as well. So with these, I'm going to say don't worry about using limits so much. Let's see. This one also, similarly, if it's defined as x with a, but approaches infinity as x approaches b, we define that. Okay, yeah, that's basically the same thing. It's just so an example. Let's do an example that might actually. Let's see. Let me go here. So if we would have had going from 0 to 1, 1 over x squared. Let's take that one we just did, right? This one, no infinities set, but let's just play with it. If you integrate 1 over x squared, we did this, that's x to the minus 2, right? We add 1. Well, actually, let's go ahead and take that step. This is 0 to 1, x to the minus 2 dx. We add 1, so we're going to get x to the minus 1 divided by negative 1. And that's going to go from 0 to 1. We're going to rewrite this with the exponent down there, so that's negative 1 over x, going from 0 to 1. When we plug in 1, we're okay, negative 1 over 1. When we plug in 0, though, whoops, what happened here? 1 over 0 is undefined, or remember from our picture, it diverges, it goes to infinity. What's 1 minus infinity? Well, it's still infinity, right? So this thing diverges, and we see it right here. So that was one of the examples of diverging stuff. So we just get to say, hey, this diverges. And when they ask for, so they, again, on these, they'll ask for two things, converges, diverges. So we say diverges. And then the second part, it'll ask what the value is. Of course, it doesn't have a value, so you put D and E. The instructions will tell you to do that. Does not exist. So this is like the A part answer. This would be the B part answer for this one. Okay. And again, we didn't have to use the whole conception of limits. We used the part that was important to us, that we know, okay, division by 0 goes to infinity, that diverges, or the ones that converge. 1 over infinity, that goes to 0. That's all we're doing without having to implement a lot of additional notation. And again, in the business world, your boss just wants to know, or you want to know, maybe you are the boss, you want to know what's happening, you want to know those values. You want to know either it diverges, we don't have an answer. You don't care about all the notation that was used, you just want to know. Right? If you're doing it for a math paper, okay, then we got to write all these things up because you're publishing it to a different audience. That's one of the things you find as further along you go. It depends on which audience you're talking to how you have to write things up. You're talking to business folks, we just need to make a decision on this and either say yes or no, or build the factory or don't build the factory, or build it half the size or twice the size, or that's what we need to know. We don't need to know all the intricacies of the calculation. And that's pretty much all we have to worry about. So let me let's see, let's go. I got some room here. I want to, let me do one that was similar, just if I can think of what it was. I think it was something like this, going from 0 to infinity. And I think it was, I think you'll see it, it was 1 over cube root of x. I think it's in the homework like this. Okay, so 1 over cube root of x. How do we rewrite the cube root of x? What's the exponent that we use? 1/3. Since it's in the denominator, we use negative 1/3, right? So we're going to rewrite this as going from 0 to infinity. X to the negative 1/3. When we integrate that, what do we get? Again, we're going to add 1. So if it's 1/3, what we're going to add is 3 over 3. That's another way to write 1. So negative 1 plus 3 is positive 2. So this becomes x to the 2/3 over 2/3, right? And this goes from 0 to infinity. I might have those limits wrong, but anyway, yeah, I think I'm probably off. I think it goes maybe 0 to 1 or something in the homework, but we'll just do it this way. So what you do is, okay, 2/3, a fraction of the denominator, if you invert and multiply. So this is going to be 3x to the 2/3 over 2. Again, going from 0 to infinity. So then we get 3 infinity to the 2/3 over 2 minus 3 0 to the 2/3 over 2. Now this one, does this converge or diverge? It diverges because the infinity to the 2/3 actually does go to infinity. Okay, so that diverges. It's not one of our, remember, we only have 2. Either we divide by infinity, that goes to 0, or an exponent with a negative. And this doesn't have a negative anymore. It used to when it was when it was in there, when it was in the integral, but it's not negative anymore. So that goes, so this diverges. And again, I think in the homework they have maybe from 0 to 1, so you can just plug those in. But this one diverges. But I also wanted to help you with the cube root of 3, just to know that's a 1/3, and then you add the 3 over 3, and you get there. And this part here just goes to 0, right? 0 to the 2/3 is 0. Times 3 is 0. 0 divided by 2. So this part is 0. But when you have one part that diverges, the whole thing diverges. Okay. So you got basically infinity minus 0. Well, that's still infinity. That's still diverging. Okay. But I think in there, maybe it goes from 0 to 1. So the 0 disappears, but then you'll see it. A little different. But at the same time, we didn't ever really have to worry too much about limits. But it's like we're looking in here, if you say, oh yeah, if I plug in 0 at this point, I'm in trouble, right? Because I get a division by 0. But like I said, just don't worry about it, because once we integrate it, it's not division by 0. Okay. So we don't have to use all the special techniques, but we do need to be able to integrate and then plug things in. And again, just a brief review of the limits, but just picture what the limits mean. We don't have to use all the notation. Okay. Questions? I think there's like only 5 or 6 problems. I think there is one word type problem like what we did, but then the other ones are pretty just straightforward. They're going to infinity or something. I worked a few of them. And again, you just tell it whether it converges or diverges. If it converges, then it should be a number that it goes to. Just be careful. A lot of times you could work it out on your calculator, but it gives you a decimal, and they don't accept, WebAssign doesn't accept the decimal answer. It has to be as a fraction. So just be able to work them both ways. Um, but other than that, that's pretty much it. It provides a pretty good overview. So for the final exam, what to expect is there will be one question out of each of these last three sections. So do know how to take right. So for the whole class, yeah, you need to know how to take the derivative, get the antiderivative, use the fundamental theorem. So both those are the two main topics we had is getting the derivative, which gives us a rate, starting with the rate and integrating the antiderivative, which gives us an amount. So we went back and forth, but also be able to do consumer and producer surplus. That was what we did on Tuesday. They will provide the formula for you, so you don't have to worry about remembering it, but just kind of remember one is P minus and then the other one is that minus P, but we will give you the formula on that. What did we do? Average. They'll ask for what is the average, and so that's the integral, and then you use the fundamental theorem of calculus, but you also divide by the interval, right? B minus A. So that was the only thing with that. So those are the last three that we haven't tested you on. Go back and review test 1, 2, and 3. There are some questions on the final that are actually that you could take off the exams, the template of how they had you do it, and it's right there. It's just got a different function in there. But yeah, sometimes like there'll be one where they ask you about minimum and maximums, critical points. We had an exam question. The final exam question looks very similar, except it's a different function. But the process of doing it will be the same. Find the derivative, set the derivative equal to 0. Those give you your critical points. But then remember, go back to the original function to plug it in to get the minimums and maximums. And also check your endpoints. Okay, so look over all of those type of things. And just again, review each exam 1, 2, 3, and the reviews for each of them. Those will give you some extra questions to work through. But you'll see that the final exam is not, you've seen it before. You've seen it 3 times basically with each of them. And again, there'll be 10 multiple choice, 7 open answer. Fill in the, where you show your work and all that kind of stuff. Thursday night, 7:10 p.m. in some other place of campus. I can't remember where it's at, but it's in there. I think LSE. I will have 2 assistants because there'll be 2 classes, so it's 180 of us will be there. So I'll have some help passing them out and collecting them, and watch for an announcement I'll put out probably for Tuesday afternoon around 3 or 4. I'll be available for Zoom. If you need some other times, just contact me, and as I'm available, I'll work it in as best I can. Now it's just you've got everything you need. Just kind of review if you've done, and remember, doing well on this will replace a lower score on either 1, 2, or 3. And typically, you'll see it's so similar. You should do at least as well as you did on all the 3, probably better. And that's why we can, because you've learned this stuff. You stuck around and you've learned it, and go back and review it, and it'll all be good. Any questions? All right. It's been great working with you. You're free to stick around for another half hour if you'd like. I'll be here. I have no place to go. If you have any questions, we can work on things individually. Again, it's been a pleasure working with you all.